Hello, Chem 111. This video is about valence shared electron pair repulsion, or VSEPR theory. And right away, you might notice that really it should be called VSEPR, but it's not. So this video is about the most basic shapes we encounter in chemistry. There's a second video about slightly more complicated shapes. And since this is the first video in the series, I'm going to first explain what a steric number is. So a steric number of an atom, and generally this is a central atom in a molecule, is the total number of atoms plus lone pairs attached to that atom. And so I'll just go through examples of steric number 2, 3, and 4, and you can see some different examples of this. All right, so we'll start with steric number of 2. All right, so, and just to be clear, the theory behind VSEPR, I'm going to leave that for your discussion in lecture. This is really just all about how to identify these shapes once you understand what's going on. So here's an example of a central atom with a steric number of 2, the molecule CO2. So the carbon is the central atom, and it has 1, 2 atoms attached to it. It has a steric number of 2, and so the geometry of something with a steric number of 2 is linear. And there are two choices for a central atom that is attached, that has 2 bonds on it. So if it, as you'll see in a moment, those atoms could be in a straight line, linear, or they could be bent. For a steric number of 2, VSEPR works on those atoms and lone pairs getting as far apart from each other as possible. The farthest apart these two things can be is 180 degrees. So the geometry is linear, which is just as I've drawn it on the page. Okay, so steric number of 3. And I will give 2 examples here. I'll give 2 examples that are actually related. So one is nitrate. And I'm actually going ahead now, and you'll notice I'm starting to draw things not at right angles, and that's because once we start doing VSEPR, we can see that in fact things really aren't at right angles. So nitrate, and if for completeness I need to show the formal charge, it is also true that nitrate has 2 equivalent resonance structures. I'm not going to draw them here just for simplicity. But here, nitrogen has a steric number of 1, 2. It has 3 atoms attached to it, no lone pairs, so it has a steric number of 3. And the geometry of this steric number 3 is trigonal planar. Trigonal because there are 3 things, planar because all 4 of those atoms are in the same plane. And in this case, they're in the plane of my screen, the way I've drawn them. Okay. They are evenly spaced from each other. So in a trigonal planar species like this, the angle between these things, the whole circle has 360 degrees. And so the angle between these things in trigonal planar is 120 degrees. I could draw up here 180 degrees. Okay, so that's example number 1 of a steric number of 3, the trigonal planar geometry. Now, once we move beyond steric number of 2, there are more options. So we could have central atoms, for instance. So we can have another example of steric number of 3, which is nitrite. Nitrite is a molecule that looks like this. It also has a resonance structure. And so nitrite is NO2 minus, and I would just say +1 resonance structure. You still need to draw resonance structures if you're drawing Lewis structures, but since I'm just figuring out the shape, I'm going to take a shortcut. This also has a steric number of 3 because steric number is atoms and lone pairs. So here's a lone pair. That's 1, 2, 3. Has 3 things around it, so it's a steric number of 2. So because it has a steric number of 3, it still has a trigonal planar geometry. However, the shape of this molecule, when we define the shape of the molecule, we do it, just see what color I haven't used yet, I'll use yellow. So the shape of the molecule, and I'll just write here, it's the shape of the molecule is defined by the atoms only. So the lone pair is critical because it gives nitrogen a steric number of 3 in this molecule, NO2 minus. It makes the geometry trigonal planar, but when we go to name the shape of the molecule, we just look at those 3 atoms. And as I said up top with the linear one, there are 2 choices when you have 3 atoms in a row. They can be linear, like up there, or like this one, they can be bent. Okay? So a molecule like this that has a steric number of 3 with 1 lone pair and 2 atoms, it has a trigonal planar geometry around the nitrogen, but the shape of the molecule is bent. And for these 2 examples up here, the shape has the same name as the geometry. When everything is an atom, the shape has the same name as the geometry. Okay. So that's steric number of 3. You'll, I'm sure, talk about this more in class. In fact, once you start adding lone pairs, the angles aren't exactly the pure 120-degree angles, but I will leave that to your lecture. Okay, so steric number of 4. So we'll start with the first example. And again, we're going to start with the first example. That is all atoms. And so we'll start with methane, which is CH4, and this is how we draw the Lewis structure. And just to be clear, it has 4 atoms around it, 1, 2, 3, 4. So the geometry, it turns out the geometry that gets 4 things as far away from each other as possible is tetrahedral. And this is something in class, we'll look at models. You can build a tetrahedron with your model kit. We'll take 1 black atom and put 4 bonds with white hydrogens around it, and that will give you a tetrahedral geometry. I'm going to show you, here is how chemists draw a tetrahedron. So the shapes above were planar. And so we could just draw the 2 trigonal planar shapes. We could just draw them on the screen because if we choose the molecule lying in the plane of the screen, we can draw it completely accurately. It's a 2-dimensional species. A tetrahedron is 3-dimensional. So we have a special language to draw these. We draw the carbon in the middle. We draw 2 of its bonds in a plane. You might remember, think back to high school geometry, 3 points determine a plane. So carbon and any 2 hydrogens will be in a plane. So I'm going to pick the plane of the paper for this one. And then we show a hydrogen coming out of the plane with a wedge, and we show hydrogen going back sort of behind the plane of the screen with a dash. And so I'll just annotate those with their names. So this is the wedge, and it is coming out at you. And this is the dash, and it's going into the page or the screen. Okay. The angle on a tetrahedron is, oops, I want pink for my angles, is on a pure tetrahedron is 109.5 degrees. And that is actually a pretty useful angle for chemists to know. So if you go on to organic chemistry, you're definitely going to need to know this. You should know it this semester, but of course, everything's open, book open note. You could always come back and watch this video. All right, so for this example, because everything is an atom, tetrahedral is also the shape. You can also, if you don't want to see, tetrahedral is a good name for the shape. It is a tetrahedron, but we'll just go with that. Okay, so that's example 1 for steric number of 4. The second example has one lone pair, and that would be something like NH3, ammonia, which has a lone pair. And so this, again, has a steric number 1, 2, 3, 4. So it still falls under our tetrahedral geometry. I'll write that again just so we're clear. So the geometry is tetrahedral. And to name the shape, it's helpful to look at it. I should say as well that what I have just drawn, if you draw a Lewis structure for ammonia, this is still the Lewis structure. Okay, we don't always draw our molecules with the correct shape when they're three-dimensional because it takes a lot of work. And as you can imagine, if you had a large molecule, it would get just really overwhelming figuring out what's going forward and what's back. So we draw it as, kind of the bottom of that tetrahedron. We can put the lone pair anywhere. I'm just choosing to do it that and sort of show my lone pair looking kind of like a balloon up there. And again, this is really helpful to build with your model kit. I'm sure you'll do that in class. But what you have is a pyramid, but the nitrogen is sitting above the hydrogens, right? So it's not down in the plane with all of them. So this shape is a pyramid. It's a pyramid that has a base with 3 sides. So I could just show you that. There's a side here, and a side here. So we call that a trigonal pyramid. And students sometimes get confused between trigonal pyramid and trigonal planar. Trigonal pyramid is not planar. Okay, it is a 3-dimensional structure. Trigonal planar back up here is in fact planar, as the name suggests. So it's really important not to call this one planar because it's not. And you can see that with your model kit. Okay, the final example I'll show with steric number 4 is water. And water, H2O, has a steric number of 4 around the central atom with 2 lone pairs. So 1, 2, 3, 4. So the geometry is still tetrahedral. And we can actually draw this without getting all fancy and 3-dimensional because it's only 3 atoms. And again, 3 points determine a plane. So in fact, we tend to draw it just the way I've shown it right there. If you want to make it look 3-dimensional, which, there's very little reason for you to do, honestly, but, you could have it like this, and then you have a lone pair sort of going back and a lone pair up here, but you don't need to do that. The Lewis structure itself looks just fine. And that shape, again, you have 3 atoms. They're definitely not linear. And so this shape here is called bent. And you might say, well, wait a minute, we had a shape that was bent up here way back with nitrite. That one was bent. And this one was bent based on a trigonal planar geometry. And so, as I said, the angle there, it's actually not quite 120 degrees because of the lone pair, but it's close. This angle is also not quite 109.5 degrees, but it's close to that. And so we use the same name for 2 shapes that are actually not quite the same in terms of angles, but they are both bent. So really what we care about in those shapes is Is a molecule with two atoms on it, is it bent like water or nitrite, or is it linear like CO2? All right, so those are the steric numbers of 2, 3, and 4.